So coming back to formaldehyde, we need to think about what's happening with we have one leftover orbital. And to visualize this, we actually need to take our molecule, we're sort of looking at it from the top side, we actually need to like tilt it over onto its side. So I'm going to draw it this way, where our carbon and oxygen are here. We've got our sp2 hybrid orbitals here that are overlapping. And we have some other sp2 hybrid orbitals here. These are our lone pairs. And we have our hydrogens over here. So I've taken the molecule and we've sort of flipped it over so now it's laying flat. All right, so I'm trying to show that with my hand here, right? The molecule is now where the carbon, oxygen, and hydrogens are all flat in the same plane, because this is a trigonal planar structure, so they're all going to be in the same plane. So I now need to do this because this is where the other p orbital is. The p orbital that is not part of the hybridization points perpendicular to the other orbitals. So I'm actually going to draw it in a different color here. So we have one p orbital on the carbon, and I'll do yet a different color, another p orbital on the oxygen. Right, so these are the leftover p orbitals, one on a carbon, one on oxygen, that were not part of the hybridization. And right, so these each would have one unpaired electron left in them, and these are going to form a hybrid. So not a hybrid, they're going to form a bond. So we can sort of visualize these stretching over. Let's use a third color, do yellow. We can visualize these merging together above and below here to form what we call a pi bond. Now, the reason for sigma and pi is that it's a little bit like S and P, except for in Greek. So that's where these letters are coming from, because a pi bond is kind of like a p orbital, and a sigma bond is kind of like an s orbital. Kind of. What makes a pi bond is that the electrons are not along the internuclear axis. So in this case, they are above and below the internuclear axis. Now, one thing to be careful with pi bonds is that this may look like a triple bond. You may see, oh, I've got a bond here in the middle, and a bond here at the bottom. But the thing to remember about pi bonds is that, much like a p orbital, these are just two parts, the above and below, that are part of the same bond. So you only have one pi bond here, which is both of these parts. So this has two electrons in it, spread across both lobes, much like a p orbital, right? The electron's not like going back and forth, it's a wave, and it's in both places. So that's where the electron density is above and below. And then there are two electrons down here in the sigma bond. Let me do that in a different color, if you can read that. So there's still just a total of 4 electrons, just like we would predict. 2 of the electrons are in what we call a sigma bond, where the electrons are in between the two nuclei, in between the two atoms, and 2 electrons are in this pi bond, above and below the molecule. Now, one consequence of this is that it doesn't matter so much in formaldehyde, but you can't actually twist this bond. When you have a pi bond, this is a rigid bond. With sigma bonds, there's nothing preventing the molecule from twisting on either side. But with a pi bond, having those electrons on the top and the bottom, if you twist one relative to the other, that would cause the overlap to go away, and you would no longer have a double bond. Now, for formaldehyde, this doesn't matter so much, but let's look at another molecule where it would matter. Let me think of a good one. Okay, so let's look at a molecule like this. There we go. All right, so this molecule is called 1,2-dichloroethene, or dichloroethylene. Anyway, the naming doesn't matter for you. What we need to look at is what's happening with the orbitals here. Right, if we draw the Lewis structure completely, putting all the lone pairs, our chlorines are going to have 3 sets of lone pairs on them. Okay, so what's happening here in terms of the bonding? Think about valence bond theory. Well, so one thing to know when we're looking at these overlap of orbitals to form bonds is that any single bond will always be a sigma bond. So all of these bonds here, 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 and here are all sigma bonds. So they're all going to be along that internuclear axis. That's always the first type of bond that forms. When you have a double bond, that's going to be first a sigma bond, and that's going to form from the hybrid orbitals overlapping. And then with the leftover p orbitals, you're going to form a pi bond. So one sigma bond plus one pi bond. And we'll see in the next video, if you have a triple bond, I'll just write it here for completeness sake. It's going to be still one sigma bond, but we can form two pi bonds. Right, and that describes what's happening with the molecule here. Okay, so what does this look like for this molecule, dichloroethylene? So from this perspective, we can look at the hybrid orbitals. So again, we're going to have, again, because we have three, let's count them up, 1, 2, 3 bonds around this carbon, and no lone pairs. This is going to form a trigonal planar structure, just like we've learned with Vesper theory. But we can also describe this with sp2 hybrid orbitals. Let me just draw those a little bit bigger to give myself more space. I don't think I actually achieved my goal. There we go. All right, those are a little bit bigger. All right, but these are sp2 hybrids. And the additional p orbital is pointing up and down. So it's kind of hard to draw, because we're looking down at the molecule. So on the top side, we're going to have an overlap with a 1s orbital from hydrogen. On the bottom side, we have our chlorine, and it's going to have a hybrid orbital that overlaps along with our, this will be sp3 hybrid orbitals because it has 4 electron domains. So the geometry tells us, right, the electron pair geometry tells us what type of hybridization it has. So the fact that it's tetrahedral geometry means it has sp3 hybrid orbitals. Those go together. So we don't have to, you can think, this is sort of adding on to what we already know from Vesper theory. So I'm not going to draw them, but there's going to be 3 other orbitals that are just for all the lone pairs spread out evenly in a tetrahedral geometry. Now our other carbon is also going to form, I'll do it in red, it's also going to form these sp2 hybrid orbitals, and we're going to line them up so we get a sigma bond here. And then we'll have our chlorine on this side, which is also going to form sp3 hybrid orbitals. Again, I'm not going to draw all of them just to keep the visual clutter down. And then a 1s orbital that's from our other hydrogen here. All right, so again, similar to what we did with formaldehyde, we can now take the structure and flip it to its side so that we can look at the leftover p orbitals. The leftover p orbitals, again, are going to be pointed straight up and down. So if we take this and rotate it so that it's lying flat. So all of this is a plane. These are both trigonal planar structures, so we're going to turn it over like this. So again, we're going to have our sigma bond that's forming from the overlap of the sp2 hybrid orbitals here. And we have our hydrogen coming out this way, our chlorine, and I'm not going to draw all the orbitals here. All right, but now this is flat. And again, we're going to have our p orbitals that point up and down. And these are not part of the hybrid. And just to make it a little bit clearer and not have too many lines here, I'm just going to draw, let's use green. We're going to have our pi bond form above and below. So again, this is going to have 2 electrons in it, and they're both above and below. They're not sort of moving back and forth between it. This is like a p orbital. All right, now this is where the fact that we can't easily twist this molecule becomes relevant. So, in fact, I drew these backwards. These over here, to keep with the structure that I drew up above, the chlorine should be in the back and the hydrogen should be in the front. Okay, and that's relevant because if we could twist this molecule, it'd be very easy to switch where the chlorines and hydrogens were. But the only way to twist this molecule is to break the pi bond, right? If we turn everything 90 degrees, like this, so I'm going to keep the left side the same. have our sigma bond here, but we could twist this such that the chlorine is pointing up and the hydrogen is pointing down. What we have is that we have one p orbital here and the other p orbital is pointed 90 degrees apart, and there will be no pi bond. So this is what would happen if this molecule tried to twist. You'd have to break this bond. And so what happens is that this molecule will stay in the structure where the chlorines are on opposite sides here. If we could twist it, then this chlorine could come on the same side. And so those two are actually different molecules. We call them isomers. So what that means is if I draw a structure like this, HC chlorine here, so this is the molecule we have been looking at. And the opposite version where the chlorines are on the same side, because we can't twist, these are not the same molecule, right? One we had to twist to get to the other version of it. So these are what we call isomers, meaning they have the same number of atoms, but the arrangement is different. And these are what we call geometric isomers. Make sure I have the right name there. Well, it's not here in the textbook, but anyway, this is one of the consequences of this valence bond theory, is that these are isomers and these are not equivalent. So we can't easily just twist, say, this side around to get to this side because we'd have to break this pi bond. All right, so that's some of what's going on here. So how we can form single bonds, double bonds, have pi bonds, and in the next video we'll look at a molecule that has a triple bond, and what does that look like?